So we have covered 4 mechanisms in this chapter. E1, E2 for elimination, SN1, SN2 for nucleophilic substitution. Which reaction will the reaction undergo? It really depends on lots of things, which include the structure of the R group. Do we have primary, secondary, or tertiary R groups? The leaving group, is leaving group a good one or not so good one? The nucleophiles, is nucleophile a strong base or not? And the solvent. So we will take a look at this effect one by one. First, let's look at nucleophiles. Nucleophiles are Lewis bases. They are the anions or the atoms with lone pairs of electrons. So they are seeking nucleus, or they are seeking positively charged species. There's a term called nucleophilicity, which describes the nucleophilic strength of a nucleophile. This is a measure of how fast the Lewis base displaces a leaving group from a suitable substrate. There are some criteria that I want to describe here regarding the nucleophilicity of the nucleophiles as opposed to its basicity. Generally speaking, if we have a neutral molecule that serves as a nucleophile, it will be relatively weak compared to its anion. For example, water will be a weaker nucleophile than hydroxide, and ammonia will be a weaker nucleophile than amide ion, NH2-. The second rule, in the same row of the periodic table, the more basic means the more nucleophilic. For example, amines will be more nucleophilic than alcohols. This deals with the electronegativity of the atoms. So now we are comparing nitrogen to oxygen. Oxygen is more electronegative, so it will hold the electron density tighter. The electron will be less available to attack on something else. As a result, alcohol will be less basic and less nucleophilic. So, in the same row of the periodic table, nucleophilicity and basicity are in the same trend. They are the same pretty much. And in the same column of the periodic table, that's not true anymore. Smaller ions are less nucleophilic. So for same column, the size will matter. So here are the nucleophilicity of different ions in the same column. The larger ions will be more nucleophilic than the smaller ones. This is because smaller ions are solvated, suppressed. They are surrounded by solvents which will shield their electron to be available to attack on something else. Lastly, just want to give you some examples of good nucleophiles because many of you have asked me about this. So cyanide ions are good nucleophiles, and hydrogen sulfide or alkyl sulfide ions are good nucleophiles, and iodide, good nucleophiles. Okay, they are not very basic, and the negative charge is stabilized. So when you see these good nucleophiles, you should consider SN2 mechanism. Okay, next, let's take a look at the solvent effect on the rate. SN1 reaction will react faster in polar solvent. Polar solvent is able to support separated positively and negatively charged species. SN1 has carbocation as an intermediate, so it's a charged species and it's more stable. Carbocations will be more stable in polar solvents. And the polar solvents can stabilize the charge-separated transition states, which will lower the activation energy and increases the rate of SN1 reaction. So not only the intermediates, the carbocation will be stabilized by polar solvents. The transition state are charge-separated. They are stabilized by polar solvents as well, so the activation energy will be lowered and reaction will go faster. So SN1 reacts faster in polar solvents. For SN2 reaction, it will react faster only in polar aprotic solvents. SN2 does need polar solvents, but not all will work. Well, polar solvents are required because we need to dissolve all the reactants. We need polar solvents to stabilize the charge-separated transition states. We talked about protic solvents before. Protic solvents have OH groups, which allows them to form hydrogen bond to anions, to nucleophiles. So the solvation effect will suppress the nucleophilicity of the nucleophiles, and the protic solvents are not good for SN2. On the other hand, aprotic solvents are the ones without acidic protons, no OH groups. Aprotic solvents will solvate less, which means the reaction will be faster because nucleophiles are good in aprotic solvents. Reaction will be faster. We have learned some protic solvents, water, alcohols, right? Here I just want to give you some examples of the polar aprotic solvents. The first one is DMSO, dimethyl sulfoxide. And here is the structure, 2 methyl groups attached to the sulfur-oxygen double bond. The next one, DMF, N-dimethyl formamide. 2 methyl groups attached to the nitrogen, which is linked to an aldehyde functional group. This is actually an it's an amide. It's a formamide. The third one, CH3CN, acetonitrile. So these three are very commonly used polar aprotic solvents for SN2 reactions.